Hey everyone, this is going to be part 2 of section 4.6, graphs of rational functions. We're going to first start off by introducing a new term. So an end behavior model, or an EBM for short, tells us that functions behave like the functions that result from the leading term of the numerator divided by the leading term of the denominator. Okay, so we're kind of thinking like, what's our end behavior doing? Well, if we look first at A, okay, my lead term in the numerator is 3x squared. My lead term in the denominator is 5x squared. So if I divide those, 3x squared over 5x squared, that's going to give us 3/5. So what this is saying is that long term, our function is going to behave like the horizontal line y equals 3 over 5. Okay, and that should make sense to us because if we're finding horizontal asymptotes, we know that horizontal asymptotes, when our degree is the same in the numerator and the denominator, it's just the ratio of the leading coefficients. So long term, it's behaving like this horizontal line. Okay, well, what happens if our degree in the numerator is higher than the degree in the denominator? Before, we've always said that we don't have a horizontal asymptote, and that's true. But that's actually going to introduce a new type of asymptote called a slant asymptote. This really is doing something else, and we can determine what this function's behavior is like by looking at these terms. So if I divide 5x squared by x, that's going to give me, okay, it's going to cancel an x. It's going to act like 5x. So long term, this function is going to look like y equals 5x. Okay? I should mention that this last one was a horizontal asymptote. Okay? This one in this case is not going to be a horizontal asymptote because it has an x with it. So this is going to be an oblique asymptote. Looking at our next one, if I'm looking at x squared and then x to the third, okay, well, if I divide that, okay, that's going to be 1 over x. And then I know long term, if my x values get really, really, really big or really, really small going to the left and to the right, my denominator is going to get large. This is going to act like 0. So our horizontal asymptote is at y equals 0. And again, that should make sense because the degree in the denominator is higher than the degree of the numerator. And then for our last one, we have x to the 5th, and then we have an x cubed. Well, my degree in the numerator is higher, but long term, this function is really going to act like x squared. Okay, so again, we have our horizontal asymptotes showing up. Okay, and that just means that long term it's acting like a horizontal line. However, our other functions, we have other types of asymptotes. And I've gone ahead and I've illustrated this on Desmos for us. So taking a look at that first one, here was our function, our rational function. We said long term it's going to act like this horizontal line. And I see that if I zoom out, yeah, the end behavior, it looks just like that, okay? The next one, the degree in the numerator was higher than the degree of the denominator, okay? But long term, if I zoom out, this function's going to look just like the line y equals 5x, right? It's like I can't even see anything else. If I zoom out and I keep zooming out, it just basically looks like this line. Okay, if I look at my next one, okay, our degree in the denominator was higher than the degree of my numerator. Let's zoom back in, okay? Long term, though, this function is going to look like the horizontal line y equals 0. That's our end behavior. If we just keep going out as far as we can, it just looks like that horizontal line. Okay, and then our last one again, we had our degree of the numerator was higher than the degree of my denominator. Let's see. Lost sight. Okay, here we go. So our function looks like this, okay? But long term, I see that it's going to act like a parabola x squared. So if I zoom out and I keep zooming, I can see that my end behavior on the left and the right is going to just approach that parabola. So we don't always have horizontal asymptotes, but long term, our rational function can act like other types of functions. So that's going to be what our lesson is about today. Okay, so how we find oblique and slant asymptotes, that's going to occur when the degree of the numerator is higher than the degree of the denominator. And how we find them, we're going to use long division to divide. Okay. So that's going to lead us into our example here. So we're going to identify the asymptotes and the intercepts of the function, and then we'll graph and describe the end behavior of the function using our limit notation. Okay, so our function that we have is x squared minus 3x plus 2, and then that's over x minus 3. So a couple of things. If I factor my numerator, let's see, I'm going to have x minus 2, x minus 1, that's over x minus 3. So no holes because nothing's going to cancel. I know that I'm going to have a vertical asymptote at 3. So for asymptotes, vertical asymptote is x equals 3. Okay. I see that I'm not going to have a horizontal asymptote because that degree in the numerator is 2 compared to my degree in the denominator, which is 1. So in this case, I know that I'm going to have an oblique or a slant asymptote. Okay, so I'm going to have an oblique asymptote. Now the goal is we need to try to figure out what that's going to be. So I always like to use long division to help us figure that out. Using long division should also just help us rewrite this in another way that's going to help us look at maybe some function transformations or function combinations. So I'm going to have x minus 3. I'm going to divide that into x squared minus 3x plus 2. Okay, so long division, I'm thinking, what do I need to multiply x by to get me x squared? That's going to be an x. So x times x squared is x squared. X times negative 3 is negative 3x. But I need to go ahead and change the signs because I'm subtracting. So that'll get rid of my x squared terms. That'll also get rid of my x terms and leave me with a remainder of 2. Okay, x cannot evenly divide, or there's nothing that I can multiply x by to get me 2 without having to get another rational function involved. So I'm just going to write this as plus 2 over x minus 3, so that in our fraction form. Okay, so what have we done? Well, right now, I have rewritten this as x plus 2 over x minus 3. So what I have as my non-remainder is going to be my slant or my oblique asymptote. Okay, so my oblique asymptote is going to be the line y equals x. Okay, so that means that I can already start, if my goal is to graph this, I can already start graphing some things in. So I have a vertical asymptote at 3. Okay, and I have my oblique asymptote at y equals x. Okay, and really, to me, this should make sense because let's take a look at how we rewrote this function. Let's imagine x going to infinity. So as x gets super large, well, what's going to happen? Well, in this first term, this is just going to go to infinity, right? And it's going to go to infinity in the same way that y equals x would go to infinity. But what happens here? As x gets large here, this whole term is going to go to 0. So really, long term, this function is looking like y equals x plus 0. So that's why our end behavior is the way that it is. Okay, same thing, same argument could be made for negative infinity, long term going to the left. Okay, we're going to keep graphing this. Next up, we're going to go ahead and we're going to find some intercepts. So the intercepts are our x and our y intercepts. X intercepts are going to come from where that numerator is equal to 0 or where our function is equal to 0. So 0 equals x minus 2, x minus 1 over x minus 3. Okay, multiplying over that x minus 3 would just leave me with x, or 0 equals x minus 2 times x minus 1. And so we have 2 zeros at x equals 2 and x equals 1. So again, since this says intercepts, I am going to go ahead and write those as coordinate points. So we have one at 2, 0. We have one at 1, 0. And then finding our y-intercept, that's probably helpful for us to do. That's plugging in 0 for our function. So f of 0 is equal to 0 squared minus 3 times 0 plus 2, or 0 minus 3. So let's see, that looks like that's going to be negative 2/3. So there's our y-intercept. Okay, we are going to go ahead and we're going to graph this function. So let's go ahead and make ourselves a little table. Okay, my vertical asymptote is at 3, so let's choose a couple of numbers going a little bit to the left, a little bit to the right. So 0, 1, 2, 3, 4, 5, and we'll start up there. Okay, so I know that 3 should be undefined because that's my vertical asymptote. 0 was our y-intercept. We just found that was negative 2/3. If we go ahead and plug 1 in, oh, okay, well 1 was one of our zeros, so that's going to be 0. If I plug 2 in, that'll be 0. Okay, if I plug 6 in, we actually have to calculate this one. Let's see, 4 times 3 over 1. Okay, so that's going to be 6. Wow, I said, you know what I meant. 2, there we go, 2 times 3. Okay, and then plugging 5 in, that's going to be 3 over 2, so 6 as well. All right. So plotting our points, we'll do this in a different color. We'll do this in red. Okay. Okay, 0 is going to be negative 2/3, so somewhere in here. Okay, 1 is going to be 0. 2 is going to be 0. 3 is our vertical asymptote. Okay, 4 is going to be 6, and then 5 is also going to be 6. Now, okay, if I start connecting my points, these look like they're kind of like a horizontal line. It's not going to go directly like that. In this case, I think, let's go back. It does kind of swoop in. If you wanted to find maybe 1.5 and 4.5, that's going to give you a more accurate representation of our graph, but that's kind of optional. Our goal is just to go for what the shape looks like. So I think here, it's going to go in, it's going to loop, and then it's going to approach our oblique asymptote. And then same thing over here. We're going to come in, we're going to swoop in, and then come down this way. Okay, so there we go. That is what this graph looks like. Now, let's go ahead. We're going to write some limit notation. Okay, so we have the limit as x approaches. Let's do our vertical asymptote. X approaches 3 from the right. We'll have the limit as x approaches 3 from the left. And then limit as x approaches 3. Okay, that's our vertical asymptote, and then let's do end behavior. Okay, vertical asymptote, if we're looking at this graph coming from the right, well, it looks like from the right we are going up towards positive infinity. Okay. If I look at it coming from the left, looks like we're going to negative infinity. And then because one's going to positive and one's going to negative, they don't match. This limit is not going to exist. Okay, end behavior time. So the limit as x approaches negative infinity. So as my graph continues going to the left, where do we go? Well, it looks like we're also going to negative infinity. And then if we go and look going to the right, looks like we are going up to positive infinity. Okay. One thing that I'm going to go ahead and I'm going to mention now, but we're going to talk way more about in the spring, is that we need to be aware that sometimes end behavior can be written differently. Okay. So some people argue that end behavior is what you're approaching. Okay. So like in this case, we don't approach anything. We're going to negative infinity. We're going to positive infinity. Sometimes also we can argue that a limit should be you're approaching a specific value. So because we're approaching just negative infinity or we're approaching positive infinity, that's not a specific value. That just means it keeps going. Another way that we can write this is does not exist. Okay? For right now, I'm going to be okay with both. Come here in the spring, though, when we start talking about our first calc unit over limits and continuity, we're going to make more of a distinction between that. But just be aware that we can argue either the infinities or the does not exist. Okay. All right, one more example. Last one that we have here is we're going to graph and we're going to analyze our function below. Okay, so we have a whole lot of things going on here. So let's go ahead and get started. X-intercepts, Y-intercepts, domain, range, continuity, increasing, decreasing, symmetry, boundedness. We're going to talk about extrema. We'll mention all of our asymptotes and then define our end behavior using limits. So for this function, let's go ahead and factor it. We're going to have, let's see, 3x and x. I think this is going to be 3x plus 4, x minus 1. And then this will be over x minus 5, x plus 1. Okay, how does this help us out? Well, I know that my x-intercepts are going to be where my numerator is equal to 0, because that's where my function would be equal to 0. So we're going to have x-intercepts at 0, negative 4/3, and we'll have 1 at 0. Oops, wrote that backwards, hold on. Negative 4/3, 0, and then we'll have 1 at 1, 0. There we go. Why didn't anyone stop me? Just kidding. Okay, y-intercept is going to be the value of this function when we plug in 0. So if I plugged in 0 here, 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 and here, that means that my y-intercept is just going to be these two. So 4/5, 0, 4/5. Okay, before we get on to domain and range, it might be helpful to have more of a better picture of what this graph looks like. So let's go ahead and start finding some asymptotes. So looking for a horizontal asymptote, degree of the numerator and denominator match, they're both 2. So that means we're looking at the ratio of the leading coefficients. Well, that's going to be 3/1. So we have a horizontal asymptote, or an end behavior model, of 3. Okay. Vertical asymptotes are where the denominator is equal to 0. So we're going to have a vertical asymptote at x equals 5 and x equals negative 1. Okay. And since we did have a horizontal asymptote, we are not going to have an oblique asymptote. So you either have one or the other. Okay. Let's see. We found a horizontal asymptote. It might be helpful to see if our function is going to cross our horizontal asymptote or not. So how do we do that? Well, I'm basically trying to see, does this function at any point have a y value of 3? We're going to cross it. So I'm going to set this equal to 3, and then we're going to solve. I might choose to do the unfactored version just for now, because I think if we did the factored, we're just going to have to redistribute everything anyways. So I'm going to set 3 equal to 3x squared plus x minus 4. This will be over x squared, that's a squared, minus 4x minus 5. Okay, multiplying my denominator over, I'm already going to distribute, so 3x squared minus 12x minus 15. Oops, running out of room. It'll be equal to 3x squared plus x minus 4. Okay, solving our equation. I have a 3x squared on both sides. Okay, let's see. Subtract my x over negative 13x. That'll be 11. Divide. Okay, we do cross. Okay, so we're gonna cross our horizontal asymptote at the point negative 11 over 13, 3. Okay, so we will have that point there. All right, let's keep it rolling. Let's see. What else can we find without the graph? Let's go ahead and graph what we have so far. All right. Let's go ahead and put in our asymptotes. So y equals 3, there's our horizontal asymptote. We have 1 at negative 1. We have 1 at 5. Okay. We already have some x-intercepts. I'm going to go ahead and just plot those in. So we have an x-intercept at 1. We have an x-intercept at negative 4/3, so like just right barely over here, right there. Okay, and then we have a y-intercept somewhere in here. We also know that we're going to cross our horizontal asymptote here, so like right before -1. All right, now here's what's going on. We have this function, okay? I have kind of 3 sections. I have a section here, I have a middle section, and then I have an outer section over here. When we make our graph, we want to make sure that we are representing points that are kind of in all 3 sections. So our table, I hate to break it to you, it's going to be pretty large. Here we go. I might start this at -3. I have -2, -1, 0, 1, 2, 3, 4, 5, 6, 7. We'll do 8, 9 as well. Okay, quite a bit of stuff. So this is going to be undefined. This is going to be undefined. Nope, 0, or sorry, wow. It's -1, that's undefined. Okay, if you're watching this at home, I would recommend go ahead, pause that video. You don't need to watch me fill in a table, fill it in yourself, and then unpause. All right, welcome back. I filled out my table, and I already went ahead and plotted my points on my graph, so we just need to go ahead and connect everything together. So, looking at my leftmost portion, I have my 3 points. Connecting this, I know that we're going to be hugging our vertical asymptote. And then I also know that we're going to go up and go right underneath our horizontal asymptote. I know I'm not going to cross because I didn't find any points that crossed there. Looking at our middle portion, I know that I'm going to be hugging my vertical asymptote on the left. I do cross, and I already found that point. And then we're going to go to the other asymptote. And then this one, for 6, we did get 15.7, so that's like way up here. And then we kind of come down here. And then just smoothly going in. It looks like it's going to take a while to get near our horizontal asymptote there. Oops, I should put an arrow here. So this is what our graph is going to look like. So finishing up some of these points. For our domain, it looks like our domain is going to be all real numbers, except we're going to exclude 5 and -1. So we'll have -infinity to -1, and then -1 to 5. Oops. And then 5 to infinity. For our range, since we did cross our horizontal asymptote, that does mean that I think our range is going to be -infinity to infinity, because in that middle portion we can have any y value. Okay. For continuity, we could say that it's discontinuous, but let's actually get a little bit more specific as to what type of discontinuity. Since we have those vertical asymptotes, we're going to have an infinite discontinuity. Okay. For increasing and decreasing, we're always looking to see, okay, if I were to trace my graph, am I going uphill or am I going downhill? So I'm going to retrace over it, okay? We're always going to go moving from the left to the right. So moving to the left, I am always going downhill in that leftmost portion. In my middle portion, looks like I'm always going downhill. And then if I pick back up where I left off, again, we're going left to right. I'm always going downhill as well. So it looks like we are always decreasing. So I'm going to say increasing. Not applicable, okay, because we're never increasing. And then for decreasing, I'm going to say that we are decreasing on domain. Okay. Symmetry. Okay, let's get to that one. So our symmetry, looking at our graph, doesn't look very symmetrical. I mean, partially it does. However, if we want to test that symmetry just to be sure that it doesn't have any specific type of symmetry, we can do the algebraic test. Okay, remember that algebraic test is going to say what happens when I plug in -x. So doing that, I'm going to have 3 times -x squared plus negative x minus 4. And that'll be over negative x squared minus 4 times negative x minus 5. Okay. The negative x squareds are going to become positive, so that'll leave me with a 3x squared and then a positive x squared. Okay, I'm going to have minus x minus 4 and then plus 4x and then minus 5. Okay, so we get here. How do we determine if it is, what kind of symmetry it has? Well, we're looking to see what happened. Did all of the signs change or did all of the signs differ? Well, this is the same, this is the same, this is the same, and this is the same, but these two are different. So in this case, since not all of the signs changed or not all of the signs didn't change, we're going to say that it does not have symmetry. So all that work just really for nothing. That's okay. Okay, boundedness. Looking at this, is there any way that I could draw a horizontal line above or below any part of my function and it would contain it? I don't think so, because we have those arrows going up and down. So we're going to say it's unbounded. Okay, local extrema, if I'm looking at this anywhere, is there any part that's a maximum or a minimum? I don't think so, so we don't have any local extrema. And then last up, we have our end behavior. So the limit as x approaches positive infinity. Okay, what's going on here? Well, as we go to the right, it looks like we're approaching that horizontal asymptote of 3. And then same thing over here, as I'm looking at the left, it looks like we're approaching 3 as well. All right, that is all for this video, so I will see you all later.